Hello everyone, I'm Mohammad Teymouri, a PhD candidate at Colorado State University. This project is related to the chloride-induced corrosion of concrete structures. First, I want to thank the ACI Foundation. This project funded by ACI Foundation and supported by two ACI committee, 365 and 222. Because there is a knowledge gap right now for service life modeling of concrete structures. Also, I want to thank the Slag Cement Association for the award and the travel grant. So let's start with that. Let me give you some background about the problem. So the chloride-induced corrosion is pretty important because it's pretty common. Why? For the concrete structures near the marine area and also for the concrete pavements. I bet all of you saw the trucks that DOT sent during the winter to apply salts and brine solution on concrete pavements. These brine solutions are sodium chloride, calcium chloride, and magnesium chloride. All of this chloride can penetrate to the concrete and at the end lead to the concrete corrosion. Based on the Federal Highway Administration report, the cost is insane, and based on infrastructure card, we can see that it can impact the chloride-induced corrosion can impact a lot of structures, especially the bridges. The problem is that let me give you another background. You saw the trucks, and let's say it's sodium chloride or magnesium chloride, whatever it is. They can penetrate to the concrete. Some of them are bound, and the rest is free chloride. These can, this one is free chloride. These can reach out to the rebars and initiate something called corrosion of the concrete. Other thing is that we have two type of chloride inside the concrete. We have a bound chloride, and also we have free chloride. The blue ones are the problem. They can reach out to the surface of rebar and initiate the corrosion. So let me, this is the last slide for the background. Let me give you what is the chloride binding. There are a lot of investigation about the chloride binding. Simply, the chloride binding is a reaction with the chloride ions that penetrate to the concrete with the concrete matrix like CSH or AFM phases. And they can form something called Friedel salt. This Friedel salt is pH dependent, and when the pH of the system changes, can dissolve. So the problem is that right now for service life modeling of structures, we can consider the permeability of the structure. We can define the chloride threshold for that. The one thing that we missed, and the two committees wanted us to do the investigation, was this bound chloride will disassociate from the matrix. We cannot take it for granted. So whether intrigued by acid attack or carbonation or sulfate attack, which is pretty common for concrete structures, especially the carbonation, which is the ingress of the carbon dioxide, we can have it everywhere, and reaction with concrete phases, the pH can reduce. So here's the thing: when we have acid attack, carbonation, or sulfate attack, this bound chloride can return to the pore solution as a free chloride. It means that we have more free chloride concentration, so we have more chloride that can reach out to the rebars and initiate the corrosion. Let's see what is going on for carbonation. The carbon dioxide can penetrate to the concrete and can release some of the bound chloride that we already took it for granted for service life modeling, and we said that this bridge or this infrastructure can last for 100 years, but in the real case scenario, these can disassociate it and accelerate the corrosion of the concrete structures. This is obvious as unfavorable phenomenon because accelerate the corrosion. So we wanted to know the mechanisms and see what is going on when we incorporate different supplementary cementitious materials. This is our setup. For cementitious materials, we use type 1-2. We are using PLC or type 1L right now. I don't have the result yet, but also we use slag, silica fume, and what is called fly ash. But for this research, for this presentation, I focus on the slag and see what is going on. We use three common salts: sodium chloride, magnesium chloride, and calcium chloride. I live in Colorado. We have a lot of snow. Sodium chloride is not enough and is not effective. So they are using, for their brine solutions, they're using 85% of sodium chloride and 15% of magnesium chloride. Calcium chloride is expensive. Most of the DOTs don't want to use it. For samples, we use disc shape, water, a very common water to cement ratio, and we cured the samples for 56 days, and then we expose them to the brine solutions. We did the chloride binding test, we monitored the pH over time, and we did the chloride desorption. The main point is that to see how much of this bound chloride can disassociate over time or over reduction of pH. And we did a lot of analytical tests to see what are the compositions. So these are the materials, the composition of the materials that we use. You can see that the main difference, or one of the things that can make a difference for slag, is the high amount of aluminum oxide. When we have high amount of aluminum oxide, it can be, we can have more AFM phases, and it is helpful for chloride binding behavior and chloride desorption, which is related to the chloride induced corrosion. And these are the equipment that we use. We use a titrator to measure the free chloride over time. We monitor the pH, and we use environmental chamber and vacuum oven to make sure there is no carbonation during the test process, and a lot of analytical tests. Let me explain the chloride binding test and desorption a little bit, because it's not pretty common. So for chloride binding, we made the stock solutions. We measured the free chloride concentration before exposure with the titrator, and then we put a paste inside the brine solutions. We use 6 different concentrations, and the difference between these two, the measured free chloride after exposure and before that, is called bound chloride. We incorporated the mass of the paste and the volume of the solution. To mimic or simulate the carbonation, sulfate attack, or acid attack, which is reduction of the pH, we use nitric acid with a molarity of 1, and we use different volume of nitric acid, 5, 10, 15, 20, and 25, because we wanted to have a range of pHs over time. And then again, we measured the free chloride concentration after adding acid. The difference between these and the one that we measured for binding is called chloride disassociation. And this is a setup or the samples. Let's start with the binding. Here are the results for OPC. You can see that when we increase the free chloride concentration from 0 to 2, the bound chloride increase. And the results are influenced by type of the cation, the magnesium chloride, calcium chloride, or sodium chloride. The first observation is that the type of cation that we are using is important, because it can impact the results, right? But the aim of the study is the type of supplementary cementitious materials. When we use 25% and 50% of a slag, we can see the amount of binding increased. For example, here, for 50% slag at a molarity of 1, we can see that when we expose the samples to sodium chloride, the bounding is around 30 something. For calcium chloride, is around 50, and for magnesium chloride is around 60. You can see that compared to the OPC, it's a lot, and binding is favorable phenomenon, because it can remove some part of the free chloride from the composition and reduce the risk of corrosion. So regarding binding, we are good. Incorporation of the slag is fine, and the higher incorporation is even better. So I explained this. The main reason that we saw higher binding in, for example, in magnesium chloride, is the pH of the solution, which compared to the calcium chloride and sodium chloride is lower. Another thing is that when we use different brine solutions, they can impact the composition of the CSH, and specifically for magnesium chloride, we can see a white layer on top of the sample, which is brucite, which is very permeable and can increase the porosity and everything. One thing that I want to mention, I don't want to talk about the permeability of the slag or slag containing paste. We know that it can improve that. But at the end, when the chloride ions manage to ingress to the concrete structures, it's a different story. It's a binding, and this dissociation can happen. One more thing is that when we use slag, we saw the formation of more CSH, which is it's good for strength, it's good for durability, and it's good for binding. We can see that it's good for desorption as well. And one of the main reasons is the presence of higher amount of aluminum oxide and the formation of friedel salt. Friedel salt of a reaction of the chloride ions with AFMs and the formation of a salt which is called friedel salt. It's a chemically bound form of the chloride. We run a lot of XRD and TGA tests before exposure to the brine solution, after exposure to the brine solutions, and after acid. We can see that before exposure to the brine solution, there is no sign of friedel salt. This happens at XRD around 12 and at TGA around this area. But when we expose the samples to the brine solutions, different molarity of the brine solutions and different type of brine solutions, we can see this peak. This peak is friedel salt, and this is for SG 50% compared to the OPC. We can say this peak is bigger and higher. This is a qualitative measurement. It means that it is back up our titration result. Performance of slag compared to the OPC is better when it comes to the binding. And then this is the TGA test that we can quantify the amount of friedel salt. You can see that again for different salt and different molarities, we measured at 2 molarities. Compared to the OPC, these tips are deeper. It means that we have more chemical bonding. And then we calculated that to see how much of this binding happened. You can see that, for example, for SG50, the amount of friedel salt that we calculated based on the TGA is considerably higher than the OPC. So far, so good. So let's see what is going on when we reduce the pH, right? So when we reduce the pH, the problem with the slag-containing samples is that when we use slag, they consume most of the CH or calcium hydroxide, so the buffering capacity of the system is lower. We use different volume of the acid because we wanted to have a range of the pHs, and we can see if you check the solid ones, the solid lines are for 5 milliliter and the next one is 10 milliliter. When we have different samples, OPC, SG25 and SG50 in different brine solutions, while right after addition of the acid, the pH is very low due to the buffering capacity, it will goes up, and after 2 weeks it almost returns to the starting point. This is the starting point for NaCl. This is the starting point for calcium chloride. You can see at the end reach to the equilibrium, and this is a starting point for magnesium chloride. So even though while we have a very low pH at the system, the composition can help that everything goes back to the normal condition. But we wanted to see, we have a lot of information and investigation for acid attack on the concrete, but we wanted to focus on the chloride binding. What is going on when the pH for fully carbonated system, which is the pH is around 9, happens. We wanted to know how much of this bound chloride that I showed you in the previous slide dissociated. So again, we run the XRD and TGA, and one thing that we saw that when we added acid, for example, 5 milliliter of acid, we can see these ones are the measurement after acid addition. The amount of free chloride increased compared to the before acid. It means that some of the chloride disassociated. But how much? This is a big picture of the result. We can see the considerable portion of the chloride binding disassociated. We need to consider the chloride dissociation or desorption in service life modeling, because almost 90% of the bound chloride disassociated, return to the pore solution, and now can accelerate the corrosion. This is the result for slag 50%. You can see that the result is almost same as OPC, even though when you replace 50% of a slag. But when we have calcium chloride or magnesium chloride in the system, or the brine solutions contain these two, which is a common case in cold states like Colorado, we can see that the slag performed better. For example, for magnesium chloride, we can see that the OPC released almost 90% of the bound chloride, which is bad, and then slag only released 60% and retained 40% of the bound chloride. It means that the risk of corrosion for slag-containing samples are lower. It's depart from the permeability or chloride diffusion. We know that the slag is good for those, and actually we can see that even for the disassociation of chloride, slag-containing, even at a very high level replacement, is favorable. And we can see the mechanisms here, that we have a very high pH at the when we started. We reduced the pHs, and then we can see that it forms a lot of corroded layer on the top, but due to the buffering capacity of the system, we can see that the pH will go back to the around 10. But we need to consider something, that we always need to check the serviceability of the paste of the structure. It's good as long as it can work for us, right? So another nice picture is here. This is for sample that exposed to the 25 milliliter of the acid. It's completely corroded, but even in this case, you can see that the first layer is completely corroded. You can see a layer of the diffusion of the chloride, and still we have neat paste. So it's very important to consider that even in a worst case scenario like that, we still can have some binding and desorption process. But in general, we can say that incorporation of the slag, whether it's 25% or even 50%, which is considerable, we can have higher total binding, which is good for chloride-induced corrosion. And the released bound chloride, when the pH is around 9, which is a real case scenario, is lower compared to the OPC. These two are comparison between SG25 and OPC. At the end, we can say that the first thing that we need to consider, and the results reported to the ACI and those committees which are responsible for service life modeling, we need to consider the desorption of chloride, because it's very important. Actually, we are overestimating the life of structures, because we miss this. And another thing is that incorporation of slag is good. It can retain more bound chloride when pH reduced compared to the OPC, and the high replacement level is favorable. When it comes to the type of brine solutions, collect the samples from the DOTs. I collect the samples from Colorado State, from different cities in Colorado, and we are trying to tell them, all right, if you want to use the sodium chloride, that's fine. It's cheapest, that's fine. But you need to know you can add some magnesium chloride or calcium chloride, which can melt down the snow quicker, and also it's good for durability. Other thing is that if you have a pet at home, don't go for a walk a day before snow and a 1 day or 2 days after that. There is a researcher at Colorado State University that they're trying to have a framework for that, investigate the impacts of de-icers and anti-icers for pets. You know that a day before that, DOT sent trucks to apply anti-icers, and then after a snow they use de-icers. So don't go for a walk if you have a pet during the snowy days. It's not good for your pets. And like other studies, we have limitations. So we use pure salt right now. We are trying to use commercial ones and incorporate something called corrosion inhibitors, which is pretty common. At DOTs, they use so they send trucks every 2 hours, and when you ask why, they said, so the safety is our first priority. And you ask how about the durability of the concrete pavement, they said we put corrosion inhibitors on that, but to be honest, it doesn't help. We are started, and I have some preliminary result, but it's not complete yet. And these are the main references for this presentation. Thank you for listening, and please ask questions. Please.
Your samples were
Paste.
you said you cured them for 56 days.
Yes.
And then you did the test of the chloride. Would you consider that an accelerated absorption or corrosion testing?
So, no. The thing is that
But I mean, in the field, though, you wouldn't get those concentrations over time, so it's an accelerated test of what we would anticipate in the field. What I'm getting at is, in life cycle cost analysis in your design, mixed designs for putting in more slag, would this be an experiment you'd want to go through in testing that, or in an existing case where you're taking out cores to see if there's a problem with the thing, you can also test for life cycle assessment down the road how long this particular product will last. I'm just trying to judge that based on your test.
That's a good question. So the thing is that we didn't take samples from the field because we didn't find a lot of projects that use different supplementary cementitious materials. We cast our samples, but because we are using supplementary cementitious materials, we wanted to make sure that the hydration is enough, because somebody can say that compared to the OPC, when you use 50% slag, you need more time for curing to develop the hydration and everything.
Right.
And in a real life scenario, you have a pavement. For example, you implant everything during the summer. After a few months, you have rain or snow. They apply brine solution, and we have sulfate attack or carbonation, everything. So we try our best to mimic the situation, and we only use the result at the pH that's very near to the carbonation. But your point is correct. For example, for a bridge that already corroded, we can take core samples, we grind them, we do acid soluble test based on ASTM 1202. But this is a little bit different because we wanted to know when we have 50% slag,
right,
what is going on. Or we use a silica fume and fly ash at the high replacement level. But we didn't find any project that we can go there and already corroded, take the samples and do the test.
Well, I'm just saying in the future, can this sort of a test to be used in a mixed design to be able to project the life cycle cost when you're trying to do life cycle cost assessment, because you're doing a quick, it seems like a quick test on it.
Exactly.
It's the actual in sample is going to take a lot longer to get to some of those concentrations.
Exactly.
And so I consider that an accelerated test for something you're projecting in life cycle cost that you can then project with slag. You're getting these numbers and hopefully a life cycle that's going to be a lot longer.
Yes.
Projected. So
exactly. Thank you for the question. You are right, because for carbonation it takes a few years to reach to the pH of 9. So we add a drop of the nitric acid to simulate the condition. Okay, go ahead.
Question on the alumina content of the slag. I know it's about 15, I think, % or so. How important is that in the in the slag performance in the concrete?
It's regarding the chloride-induced corrosion. It's pretty important because one of the things that we have for chloride binding and desorption, there is a phase called Friedel salt. This Friedel salt is C3A, calcium chloride, and water. This C3A is based on the aluminum oxide in the compositions. So when we have more aluminum oxide in the composition, for example, for slag is around 15 compared to the OPC, which is around 4, we can have more FAMs or AFTs in the composition, like monocarbonate, and then they can absorb more chloride. The more chemically bound chloride or Friedel salt that we have, it means that we have lower free chloride, so it's pretty important. It's one of the main factors that can help us.
It might be interesting because that was fairly high alumina. It might be interesting to look at a lower alumina slag, because a lot of the slags are lower alumina, especially as you go more east in the country.
Great, that's a good point, thank you. Go ahead.
What is the relationship, in your opinion, between the binding of chloride and the permeability coefficient with regard to surface level model?
So I don't have the slide now, but if probably you are familiar with service life modeling. When they want to start that, they need to define two things. One of them is a chloride threshold. They put a percentage, for example, 0.4% of the cement weight. This is a threshold that the chloride can initiate. Another thing that they can define is chloride diffusion. And then for those, when you want to define the chloride diffusion, you consider the chloride binding in that. So it seems when we have a lower permeability, it means that it takes longer time for the chloride ions to penetrate. But let's say we want to build a bridge. It will last for 100 years, right? So when we have something that a low permeability compared to the higher permeability, it takes, for example, 10 years or 20 years longer for the chloride to reach out the rebars. But at the end, they will reach, right? Like, let's say not 10 years. At 50 years, they reach. So we have a lot of information, investigation on that, but you are right that when we have lower permeability, the chloride cannot reach to the concrete matrix, and we have a lower binding. That is correct. But in this project, we didn't focus on the permeability, and because of that, we put only paste to remove the noise from aggregate, and we expose them to the very high volume of the brine solutions, because we wanted to know, all right, let's say not at 10 years, at 15 years, we reach to the concentration. What is going on now? Because they overestimate the age of the infrastructures. Thank you. Okay, go ahead.
I have two questions. The first one, can you go to slide 28? I wonder if you have the results for 25% replacement for slag. 28.
Okay, go ahead.
Do you have the results for 25% replacement of slag?
Yes, I have. I didn't show it here, but this is for 50%. For 25%, let me show you here. This 72 is 81,
Okay.
and this 58 is 63. So the higher release of the bound chloride is unfavorable. The lower is better. So I only showed the slag, but it's pretty close. And compared to the OPC, is way better.
Thank you. And the other one I had, have you looked at calcium oxide chloride formations or phases in your study, or not really?
And not really, because that wasn't the aim of the study. When my advisor proposed this investigation to the ACI committees, we found that we need to focus on we didn't want to focus on the permeability or chloride diffusion coefficient or other things. We wanted to know at the end, when they reach to that level, what is going on now, because they take it for granted that we have binding and it will keep in the metrics forever.
Thank you. Appreciate it.
You're welcome.
As
Thank you.
an overall strategy, though, it would be good to look at them in
Yes,
combination.
exactly. So in one of our ongoing work, we are adding freezing and thawing cycles. Those will accelerate that. So those are the good points. Thank you.